Hey, chemistry. As we look into Coulomb's forces and how they act in different atoms, again, when we return to the periodic table and we look at Coulomb's forces within the larger scope of the periodic table, we see patterns start to emerge. And these patterns we call periodic trends. And these periodic trends can be super powerful for us as we start to look at reactivity and reactions and try to predict how this stuff is going to happen. So I want to introduce you to a couple of the major periodic trends today. And then as we look more into Coulomb's forces, we can look at how those forces affect these periodic trends. So the first periodic trend that I want to talk to you about is atomic radius. So an atomic radius is exactly what it sounds like. If we're looking at an element like lithium, we're going to see 3 protons inside of lithium. We're going to see 2 electrons in the first shell. We're going to see 1 electron in that second shell. And so atomic radius is entirely going to be looking at the distance between the nucleus of lithium and its outermost electron. And you can see the definition here. So it's the total distance when you're measuring from the nucleus of the atom to the outermost valence orbital. So after we introduce you to all of the periodic trends, we'll go back to look at these the Coulombic forces that are caused by number of protons, number of electrons, and the distance, the energy level, all of those things combined. And we'll look at how the atomic radius changes across a periodic table, left to right or top to bottom. There's a similar periodic trend to atomic radius, and that is called ionic radius. Now, we haven't talked about ions a whole lot yet, but an ion is simply an atom that has gained or lost electrons. And so one might think that an ionic radius is the same or very similar to an atomic radius. And in some ways it is. I mean, if we look at the definition of an ionic radius, it's the total distance from the nucleus of an ion to the outermost valence orbital. So the definition's almost exactly the same, but just that idea of gaining and losing electrons can cause really drastic changes in the size of the ion when you compare it to the parent atom. So after we go through all of the periodic trends and the forces that cause these periodic trends, we're going to return and look a little bit more closely at ions and see what kind of trends the size of ions go through on the periodic trend and how that compares to atomic sizes. All right, the next periodic trend that we want to define is ionization energy. And so if we go back to our model of lithium that has 3 protons in the middle and 1 proton on the outside, ionization energy would be how much energy it would take if we were going to grab onto this electron or zap this electron and get it to completely remove off of that atom. That's what ionization energy is. How much energy is it going to require to go in and take that atom or that electron and pull it completely off of the atom? That's ionization energy. The energy required to remove an electron, completely remove an electron from an atom or an ion. Okay, and then our last periodic trend is probably the one that we carry the farthest and we put it to use the most throughout this class of chemistry, and that is electronegativity. So electronegativity is the force of attraction. the force of attraction between the nucleus and its electrons. Let me give you the actual definition. How strongly an atom attracts an electron to itself. So if you look at an atom like lithium, along with all of its electrons, if there's another electron out here, whether it's an electron by itself or it's an electron that's currently attached to another atom or ion, what is the force of attraction between that atom and that other electron? How strongly can that atom attract electrons to itself? That is the idea of electronegativity. So these are the big ones that we're going to talk about. These are the big periodic trends that we're going to talk about. Now, all I wanted to do today was define these for you, and then I want to look at one of them together across the periodic table. And then later on, we'll come back and we'll look at the other couple. So for today, let's look at the atomic radius. So here is our periodic table drawn in terms of Bohr models. Again, you have this drawn. We drew this together, and this would be a really good chart to pull out and to look at right now so you can have a bigger scope than what this little piece that I'm showing to you right now. But basically, what I am showing to you is the representative elements. Notice here's my S block. And then we would find the transition elements through here. And then over on this side, I have more representative elements, and that's going to be my P block. Okay, so I've kind of taken the transition elements out of this because the transition elements start dealing with orbitals other than S and P, and it kind of screws up our trends a little bit. The D block changes the game a little bit. So before we look at how the D block is going to change stuff, let's step back and look just at the representative elements that are dealing with the S and P orbital and look at these periodic trends across it. So the periodic trend that we're going to look at together today is the atomic radius. And we're going to look at the atomic radius from the left to the right of the periodic table. So if we look at the atomic radius, the distance between the nucleus and the valence electron, notice there's a couple things that are changing from left to right. If I start with lithium and I look at the protons, for example, I have 3 protons, 4, 5, 6, 7, 8, 9, and 10. So my protons are increasing by 1 across this periodic table. Okay, another change that you guys picked up super well is electrons. Notice if I'm looking at my valence electrons, I have 1, 2, 3, 4, 5. Now, we wouldn't draw the electrons like they have drawn the electrons. We would have paired the electrons and drawn them something like this. But either way, there's 5. And then on oxygen, there's 6 valence electrons. And fluorine, there's 7 valence electrons. And in neon, there's 8 valence electrons. So looking left to right, our valence electrons every single time are increasing by 1, increasing by 1, increasing by 1. Notice another thing going left to right, there's a couple things that are not changing. Notice core electrons are not changing. Every single atom in this second energy level has 2 core electrons. Another thing that's not changing left to right is energy levels. Notice every single atom within this second energy level is going to have 2 energy levels, right? That's why it's the second energy level. So we have a couple things that are changing, protons and valence electrons. We have a couple things that are not changing, core electrons and energy levels. So I want you to pause the video here and think, how would the atom's size change going left to right? Is neon going to be bigger than lithium? Is neon going to be smaller than lithium? Pause the video here, make a prediction. And actually, we think about atoms as marbles, right? We like to think about atoms as in, like, if it gains a proton, it gains a marble, right? So if my stack of marbles is getting bigger, a lot of people would predict left to right that the atom gets bigger, but it actually doesn't. It actually gets smaller. So going left to right, atomic radius is going to decrease. So left to right, atomic radius is going to decrease. And the reason is this, because the atom is built off attraction, right? We have protons in the middle, we have electrons on the outside. Well, if I get more and more and more and more protons, the more protons I have, the more strongly it's going to attract that electron. And the more strongly it attracts that electron, the closer that electron gets pulled to the nucleus. So lithium only has 3 protons. It can attract that electron, but not very strongly. Neon has 10 protons. And so 10 protons is going to be a much stronger attraction to those electrons than 3 would be. And so it can pull those electrons a lot closer, and neon's actually a lot smaller than lithium. It kind of looks like this. If lithium is here, neon is there. More protons, more attraction, smaller radius. All right, let's look top to bottom. So let me delete a couple of the things we have written here. Okay, and we're going to look top to bottom now. So let's look in the first family. We'll look at hydrogen versus lithium versus sodium. Okay, so atomic radius, how is it going to change top to bottom? Pause here and make a prediction. So top to bottom is not quite as tricky as left to right. We do have protons increasing, right? Hydrogen has 1 proton, lithium has 3 protons, sodium has 11 protons, and that's going to cause more attraction, right? But if we think in terms of Coulomb's law, we think both in terms of a charge increase, which would be the increasing protons. We also need to think in terms of a distance increase. So notice that going top to bottom, energy levels is also changing. Hydrogen has 1, lithium has 2, sodium has 3. So the distance between the nucleus and the outermost electron is being forced to change as energy levels get added that push these electrons farther and farther and farther away. So top to bottom, the atom's radius, the atomic radius, is going to increase. Hydrogen's going to be very small, lithium's going to be bigger, sodium's going to be bigger, and the trend keeps going down. So top to bottom, atomic radius will increase because of increasing energy levels or additional energy levels, which causes distance to increase. Okay, so that is atomic radius. That's the periodic trend of atomic radius. Like I said, we're going to come back and we're going to talk through ionization energy, electronegativity, and then also the ionic radius once we get into ions. So I want you to do a little bit of prediction here before we go, just to check in, and we'll do a little bit more practice in class. So if you were going to rank the size between, let's say, silicon and phosphorus, which one of those would be larger? And let's also do silicon and carbon. Which of those would be larger? Okay, so make those predictions. Let me know what questions you have. I will see you in class.